Hello everyone, welcome back again to my channel. A long time back, I'm bringing a new topic. Actually, I was tremendously busy for my new job and my professional transition, so I couldn't make any video. But from now on, I hope I will be regular with new topics, new video. While I was busy, I was always getting some comments, many. Wishes, many things. Thank you everyone for watching my video. And I thought maybe people will not watch a lot, but now I feel like people are watching and they are getting benefited, and also they are asking questions, and I tried my best to answer all of your questions. But recently I have got a couple of requests to make a video on some topics, and especially in 2D NMR, and also like TLC plate, different types of TLC stainer, so many other things. So slowly I'll make, I promise, but today I'm going to start with the 2D NMR. So especially 2D NMR means like two-dimensional NMR. So you have to do, you have to find the structure of molecule which are like very complex. So in that case, like two-dimensional NMR or like 2D NMR normally help to identify your compound. So very first 2D NMR people normally do for the COSY NMR, that is COSY, COSY. So if you take the first letter C, O, and SY means SY coming from the spectroscopy. So COSY actually like correlation spectroscopy. That's why in short it says COSY. So I'll go details about the COSY and the all others. So in COSY, the same compound, proton and proton, is compared in two-dimensional x-axis and y-axis. And why it is done, I'll tell you. Just now know the name, like COSY, like correlation spectroscopy. Just from the name you can guess it actually correlated, like comparing to two-dimensional same compound, proton NMR, proton. That's why sometimes people also say proton correlation spectroscopy, proton and proton correlation spectroscopy. In short, COSY. And there is another name is called NOESY. It doesn't mean like it produces noise. No, NOESY means nuclear N over Hauser. So nuclear N over Hauser, O, effect E, and again spectroscopy SY. So in that case, it is NOESY. NOESY also almost similar like COSY, but detection or identification is a little bit different. I'll explain details while I'm going to erase everything, and I'll show how this is utilized to identify of the structure. Then the third one is heteronuclear single quantum coherence. You don't need to remember the name. In short, people say HSQC. Okay, H means heteronuclear, S single, Q quantum coherence, HSQC. So this is very important for the 2D NMR. This is actually taken to identify which carbon is attached with which proton. So if you have any structure, suppose you have these two protons, suppose this is A proton, and this A proton is like in this carbon. So if you number 1, 2, 3, 4, so this HA will be like connected with the one carbon. So you can easily find out this HA is really in this number 1 carbon. And definitely if you have other proton, those proton are in the number 2, other proton number, those proton are attached to the number 3. So HSQC always taken to know which proton is attached with which carbon in the same structure. I'll explain details, just don't worry. So that is called HSQC. And the fourth one is called heteronuclear multiple bond coherence, that is HMBC. So wherever people need HSQC, they always also do the HMBC. So HMBC actually determine the long distance proton with the carbon. So suppose you have a carbon like this, and you have two proton here. So so if you know this carbon, suppose you know this carbon and you need to know this number 2 carbon, so you can easily determine these protons are next to this carbonyl group. Because in the NMR structure you can see two different type proton, this proton and this proton. So now how can you confirm these number 2 carbon attached, these protons are next to the carbonyl? Why not those are next to the carbonyl? How you can determine? So that can be determined by the HMBC, like heteronuclear multiple bond coherence. Heteronuclear means like there are two different nuclear. One is carbon, another is proton. Remember this, carbon and proton, they are two different nucleus. That way is called heteronuclear, but it is multiple bond coherence. Because from this carbon, if you count how many bond you are getting, 1, 2, okay? So sometimes you can also count like up to HMBC, you can go up to 3 bond away. Like even you can get 1, 2, 3. These proton also you can get some relation, like connectivity, or like the relation. Like you will see like how once we draw the 2D NMR, then you can see like what I'm trying to explain. Okay, so that's why it is called multiple bond, and this HSQC is like direct carbon proton. So if you know like any proton, specific proton, then you can say this proton is connected to this carbon, because if you have another carbon in this structure, so suppose it is A proton, it is B proton, it is number 1, it is number 2, so you can easily determine this A proton is with the carbon 1 and B proton is with the carbon 2, that is with the HSQC. I'll explain. And these are very important tool, not only to find the structure or to determine the structure, but also some other application also. So I'll give you the reference and example like how we can use those two like for other application also. And the all are like 2D. So these 4, 1, 2, 3, 4, these 4 actually you can name as a 2D NMR. But at the last, it is, some people say 2D, but I wouldn't say it is 2D. It is not like, this is called diffusion ordered spectroscopy, or DOSY. So if you want to know what is DOSY, how to collect DOSY in the Bruker 500 megahertz NMR, so you can watch one of the video in my channel. I uploaded long time ago, and total process how to determine, how to take the DOSY NMR and how to analyze, how to determine, and what is the application. If you have any question, just ask me in that video. I'll be happy to answer that question. So DOSY NMR also kind of 2D NMR, but it is not really 2D. Like it is not called 2D, or some people say. So that's why I'm showing these 5 NMR are very important tool for determination of the chemical structure or like different parameters. So let's discuss one by one. So you can write it down somewhere, those short form, COSY, COSY, and NOESY, HSQC, and HMBC. So you can just write it down somewhere in a paper, then we will slowly discuss all of that. So now let's keep the correlation spectroscopy, or COSY. So I already have uploaded one video on COSY in my channel, so you can revisit that video also, like if you want to know, because there is a like really structure, and I try to explain how I correlate the things, but in here I'll explain a little bit shorter way, because this is very simple, but you can see really with the structure in that previous video, COSY, 2D NMR, processing and explanation, you will get it. So more elaboration is there. So now COSY. So suppose you have a molecule. So this is a molecule. So if you think how many types of proton here, so this proton is next to carbonyl group, so this is one kind of proton, and this is CH3, and this is CH2 next to the carbonyl, so this is second kind of proton, and this CH3 is away from this carbonyl also next to the CH2, so this is another kind of proton. So if you predict in one dimensional or 1D proton, so you will see this proton will show you like this CH3 has two neighbors, you will get a triplet. And then this CH2 has three neighbors, so it will give you a quartet. And it is next to the carbonyl, so it will be like if you take 0 in the NMR range, so this triplet, you will get this triplet around 0.5 to 0.6 or something. Assume that 0.5 ppm, and it will be like next to carbonyl, so it will be like around 1.9, around just so it will be a quartet. Okay, and this CH3, this CH3 also next to the carbonyl, so it will be nearby, and it doesn't have any neighbor protons, so it will not show any splitting, so it will show you a singlet, and that should be nearby this quartet because that is also similar electronic region. Okay, now so now easily I can say this is number 1 proton, and this is number 2 proton, and this is number 3 proton. Okay, but in many cases in complex structure, sometimes which proton is close by which one you cannot identify, especially the bigger natural product molecule or big molecules. So in that case, people do the COSY. So what is a COSY? COSY is like a same NMR, but it plotted one axis and another axis. Okay, so same, like it is 0, and also it will be from 0 from here. So you can say it is a triplet, and then that quartet, and then singlet. And you might have aromatic region also, like whatever. I'm just simply taking the simple example. So in that case, just make an square box. Okay, and now you can imagine a diagonal between these two corners. Okay, so this triplet, it will give you a like this in a diagonal. This quartet, it is 4 peak, so it will give you a, depending on the intensity, you will see like this in the diagonal. And this singlet, it will give you this singlet. Okay, so these are called diagonal peak, which are in the diagonal. So simply those peak, and same thing, and you can just correlate these and these, same. So same. Okay, and this is also same, and this is also same. Sorry, this is also same, and this same, and this same. So no problem. But so you will always get this peak in the diagram. In the diagonal. This diagonal of this square. Now, the correlation spectroscopy, or COSY, also gives some cross peak, that is called cross peak, that indicate this guy has a relation with this guy, like next to like 3 bond away. So who will show what. So the number 1, you can easily assume this number 1, it doesn't have any neighboring proton. No, right? So it will show just one single peak. It doesn't have any neighboring proton. But this 2 and 3, so if you see 2, that 2 proton has a neighboring this number 3 proton. Okay, so I just simply assume this way. So count bond. So if you take bond 1, this is another one, 2 and 3. So COSY always determine 3 bond away proton, like as a neighbor. Okay, so neighboring proton, they have cross peak. So these and these, they are like next to each other. So you will see a cross peak here, and also a cross peak here. So actually, we can take a single bigger peak, okay? Then it will understandable nicely. So then you can just make a relation. So this cross peak is easily indicating that it has the relation with this corresponding peak and also a relation with this corresponding peak. And similarly, it is always mirror image. So you will see always mirror image. So this is also, you can correlate this and this. That means this is a cross peak. So that means it has relation with him. So they are next to each other. So this is actually COSY. So now we are talking about NOESY, okay? Suppose this molecule, so you have 2 aromatic proton, like 2 benzene ring proton, okay? Now you clearly will see okay, so this will be your proton, like, because these 2 proton is double bonded proton or olefinic proton, so olefinic proton normally shows up above 5, so 5 to 6 or 6.5, and definitely they are neighbor each other, so they will give you a doublet. So suppose it is A and it is B, okay, and in the aromatic it is C and it is D, okay? So now we need to know first which, especially these A and B, which one A and which one is B, okay? So we can do carbon NMR, proton NMR, and then we can determine whether it is A or it is B, something like this. First of all, you can get an idea. So this proton with the double bond and also next to a nitrogen, so more electronegative, so it will be a little up, okay? Because if you have any electronegative atom nearby any proton, so that electronegative atom always pull the electron from there to itself. So in that case, that proton will be more lighter, so it will do more spinning in the proton NMR. So if you know the proton NMR Lamor frequency or like basic information, so you will know that like more electron density decreased from the proton, it will be more deshielded. More deshielded means there will not be any obstacle. So that means, suppose a proton is like this, okay, and shielding means like there is a screen in front of this, and if you give the magnetic field, so due to the shield or screen, that proton will dance slowly because magnetic field full will not working. But if you decrease some of the shielding or like screening effect, and if you give the high speed magnetic field in the proton, that proton will dance more frequently, and more dancing, it will show up more downfield. Downfield means like upper value, like upper ppm. Okay, so in that case, so this, since this proton is with the double bonded and also next to nitrogen, so you can easily assume that this is B as, okay, and ultimately there will be another, so that will be A. Okay, now C and D. Now you can determine which one C and which one D. I can say this is C, this is D, because both are singlet. Okay, it doesn't have any neighboring proton, it doesn't also have any neighboring proton. So how do you determine which one is C? Okay, so in that case, you need to do COSY NMR. So machine will take the COSY, but you just need to give the command, like you want to do, sorry, NOESY. You have to do the NOESY NMR to determine. So you have to give the command to the machine you want to do the NOESY. So in that NOESY, so you will see this doublet A, and this has another peak like this, and that singlet 1, and this singlet 1. Now, if you see any cross peak here and also cross peak here, that means you can make a relation with this. Similarly, sorry, it's too far. This, so that means this A proton is somehow making an interaction or communication with this proton, this singlet. So in that case, you can say C. Okay, and ultimately the other one will be D. Now you can ask, like, what kind of correlation? So this is actually clearly correlating with the space. So NOESY always determine the space correlation or space communication, not through the bond. Okay, COSY always through the bond, 3 bond away. It will see the other proton 3 bond away from the carbon to another carbon. Okay, but NOESY is always see the proton next to the space. So, and this proton doesn't have any other proton nearby here with the space. So definitely you can say, okay, the other person will be D. Okay, but if you could also see the peak like here. So in that case, you can determine, sorry, why am I doing this? Okay, so in that case, if you see this A has relation with this, that means you can say, okay, now actually the proton C is this and D is this. So D is neighbor, like very single, no neighboring proton, and also it doesn't have any other nearby spatial proton. Yeah, you can say there is also proton like methoxy, right? So 2-methoxy, so it will be like A, B, C, D, it will be E, and they are like kind of symmetric, so not symmetric actually, so E and F. So you will see 2 singlet near to the 3 to 4. So you will see also here like 3 to 4, 2 singlet for the methoxy, and you will see definitely the diagonal peak, and you will not see any cross peak. But in the NOESY, you will see definitely the cross peak for these two. Like you will see here, if you take NOESY, not for COSY, NOESY, you will see a cross peak here because they are also spatially, like with the space, they are close. Okay, so that is also possible. You might see a correlation in there. So I hope you understand the NOESY part. So NOESY always determine the proton next to the close by proton with a space. Okay, it doesn't matter like if it is like 3 or 4 or 5 bond away, but as long as it is close, that will be more stronger communication. Remember that, because in many cases medicinal chemistry or neighboring or like natural product chemistry, sometimes if you have something like a bigger ring, suppose if I make more easier here, so sometimes some molecule has big ring, okay, and um, suppose you have where should I put, or yeah, maybe, you know, like this, some ring, just assume that some ring. So in that case, suppose you want to determine this proton and also like all of these proton, so definitely with the COSY, and since they are like close by, so you can determine these proton slow series with the series of the proton NMR. Like, I'm just giving you an idea like how complex it could be. So definitely in case of structure elucidation, only COSY or only NOESY cannot determine your structure. So you have to check all of those things: COSY, NOESY, HMBC, HSQC, sometimes even DOSY. And also you have to check DEPT 90, DEPT 135 to determine the types of carbon and proton there. Like, so in that case, using all those tools together, then you can determine, identify the full correct structure. That's how scientists or researchers do their structure correction. So if you have any question about the NOESY, and definitely you can read, like there are tons of literature or paper or like things in the internet, Google, or like the spectroscopic books. Especially if you want to understand really good way, then you can read a book, Introduction to Spectroscopy, written by Pavia. Okay, so that book is really good. Pavia, P-A-P-I-A, most probably P-A-B-I-A. This is the writer. So his you can Google it. His book is really good to understand those 2D NMR and the basic information like theoretical background, everything. I'm just showing you the application, okay? Let's do now the HSQC. First, draw an structure. Maybe the same structure we were thinking.
So maybe here bromine, whatever, and this.
Okay, so this is a just simply this is a structure. Now you will take the proton NMR, single proton NMR, and you will see how many types of proton. Definitely this is 1, this is 2, this is 3, and this is 4, this is 5. Okay, so with the COSY, first of all, this is very important, you need to know. So you see this is an aromatic proton, right? Aromatic, 1 benzene ring. So how many aromatic proton? 3, right? That is 3, 4, and 5. Now you can take the COSY just for targeting these 3 aromatic proton. Forget about that part, okay? 3 aromatic proton. COSY. So in COSY, you can see the cross peak for these and these 3 and 4 proton, right? Because they are 1, 2, 3 bond away. So you can easily determine that 3 and 4, okay? So suppose that 3, like aromatic proton always show up around 7 to 8.5, okay? So 3 will see 4, so it will give you a doublet. So suppose this, and 4 will see 3, it will give you a doublet, but it has also another proton next in between the bromine, but very shortly it will give you a meta coupling, small quantity. So 4 will give you a like this, a doublet, but that doublet will split a small quantity this, and this 5 will give you kind of singlet, but since it is also can show C4, so it will give you a singlet type, but very small splitting a singlet. So like this, okay? So that clearly will, you can easily understand, okay, this is the confirmed number 5 proton because of the, either you will see singlet or very small splitting singlet, like doublet, very small splitting doublet because of the meta coupling. Okay, so we can easily from the structure, proton NMR, we can easily determine, okay, this is the number 5 of the aromatic proton, like this is the number 5 of this structure. Now the 4 and the 3, okay, so if you see this kind of splitting and 3 doesn't have, so you can easily determine it is 3, it is 4. And also it can be confirmed with the COSY because they are close by, like 3 bond away each other, okay? You will see, if you take the COSY, so you will see same. So if you draw a diagonal, so it will be like this, and this. So you will see the same peak in the diagonal, same peak in the diagonal, and same peak in the diagonal. Maybe a little bit here. I draw far away. You know. Yes, now we'll say like the same way, okay? Now, definitely, if you draw this, okay. So, definitely you will see these two guys a cross peak here. That means just COSY, just COSY, take the COSY for this, targeting this proton NMR. Whatever it is showing other part, it doesn't matter, just we'll come back. So COSY will determine 3 and 4 position. So definitely you will get, this is 3 and this is 4 with the relation, okay? Now, again, how can you say this is the 3 and not 4, right? Then you have to do the NOESY, targeting this, you know, this is only one proton in the vinyl side, okay, one vinyl. So that will be like around 5, and it doesn't have any neighbors, so a singlet around 5. So this is 2, right? And now if you take the NOESY, the vinylic proton will show a cross peak with this 3. So then you can say, okay, this 3 is next to this vinylic proton because they are correlating with the space, not with the bond. Okay, so space. So that 3 is definitely on this benzene ring, close by to this indole ring. Okay, so that's how first COSY will determine their neighbor each other. So ultimately you can identify the single one is number 5 and 3, 4 position. So with the NOESY you can say 2 is vinylic proton, and that will have a cross peak with the 3. So you can say, okay, this is here, and ultimately the 4 position will go there. And if you know that, and definitely it will be a singlet, there will not be any correlation with anyone because there is no other peak. So ultimately you will get the structural observation or view with taking proton NMR, carbon NMR, and also COSY and NOESY. Okay, now if we want to take the HSQC, okay, so HSQC is not like anymore cross peak, okay, HSQC is totally different. So so it will be 1. Okay, now you can say you now know the proton number, like which proton are what, like which kind of proton. Okay, so with the HSQC you can get the idea those carbon. Okay, so if you take the carbon NMR, so there is another carbon, so suppose A, B, C, D, E, F, G, H, I, J. So this is double bonded carbon. It will show up, any double bonded carbon normally show up from 120 to 160, including aromatic. Okay, so how many double bonded? 1, 2, and this is also double bonded. So 1, 2, and the 6. So total 8. So you will get 1, 2, 3, 4, 5, 6, 7, 8. Okay, and now only one carbon here outside, and any carbonyl peak that will always show above 165. So suppose somewhere here. Okay, so only one carbonyl here, you can easily determine, okay, it is B. Okay, and this B is doesn't have any proton, right? Carbonyl doesn't have any proton, but A has the proton. Which proton? CH3 as a singlet. So you will see kind of this. That means you can easily draw a line, connect it, and see. That means these number 1 types of proton with the number 1 carbon. A carbon. It is connected with A carbon. That's the HSQC. Okay. Similar way, B doesn't have any proton, so you will not see any correlation here anywhere. Okay. Now D will have a proton, right? So which one is the D proton? The number 2. So anywhere, suppose if you see here like this, so you can easily say, okay, this number 2 proton is connected with D, so this carbon is actually D carbon. Okay, same way number 3. So if you see number 3 is somewhere here and you are getting a cross peak here, so you can say, okay, this is F. And if you look here, E doesn't have any proton, right? So you will not see any cross peak here because you have to have a proton. And J, okay, J doesn't have any proton, so you will not see any cross peak for the J. Okay, and I has a proton. So which one was the I? Like number 5, right? So if you see here and it is matching this, so you can say, okay, this is the I proton, like I carbon, like 5. So proton number is 5 and carbon is I. This is carbon, right? Remember that. Okay, so H carbon, it doesn't have any proton, so you will not see any cross peak here because no proton. And G, this G carbon has a proton, so 4. So you can see maybe this. Okay, there is a relation. So you can say, okay, this is G. So as long as you have the proton, those carbon will show the cross peak, other carbons will not. So this is the HSQC. So based on the proton connection and carbon connection, you can determine which protons are in which carbon, and remaining carbon you can determine or identify different way. Number 1, if you see the carbon is above 165 to 200, that is definitely carbonyl carbon. So you can determine, okay, this is carbonyl carbon, that carbonyl carbon, and all other carbon next to the, from the 122 to the 160, they could be either aromatic, like those those carbon, remember that 122 to 160, those are like sp2 carbon, like double bonded carbon. Doesn't matter like aromatic ring or the double bonded. So you have two double bonded carbon, one is D and the C, and here like 6 double bonded carbon. So among the 6 you get three connection, and among these two you get one connection. So total 4 cross peak for those protons and carbon, and remaining carbon you can easily say, okay, those carbon are there, like non-protonated carbon. Now still you need to know the position of those carbon, like, okay, if we want to know which one is the Z carbon, which one is the H carbon, which one is the C carbon, right? Because still we need to know, like put together the things, like it's like a puzzle. So now you get some idea, a kind of skeleton structure, but still J could be these, H could be these, like you can swap the position of J or H or E, right? So that will help you by the HMBC. HMBC is multiple bond coherence. Okay, so in that case, HMBC will show you not like this. HMBC is again like a cross peak. So with the carbon, remember that with the carbon, heteronuclear. Okay, HMBC, HSQC, both are heteronuclear, carbon, hydrogen. But HSQC is directly correlating the peak, like cross peak. But HMBC now will show you some more relation. Okay, so if you do the HMBC, so definitely you know this carbon already, I carbon, right? Because I had a cross signal. So HMBC will determine like next carbon. Okay, so the carbon to the next carbon. So you can see this carbon, also see this carbon with this proton. Okay, so this proton will give you 2 bond away or 3 bond away cross peak. So ultimately you can say, you can see the number 5 will give you the cross peak with J and cross peak with E and also H. Okay, so by checking that HMBC also with the HSQC, that's why people always do HSQC and HMBC together. So I'll show you the real structure example, how we normally correlate or determine that HMBC, because if I don't show you the real structure or application, you cannot understand here. But just get an idea, like whatever the carbon doesn't have the proton, they will not show in the HSQC. Definitely that can be determined or identified by HMBC. That will show a cross peak. I'll show you the real example with the spectroscopy, then you will understand. So hopefully till now 2D NMR is done, you understand the whole thing. Now although the DOSY is not a 2D, since I wrote here, so I can just show a little bit here. So if you're taking any NMR or you're doing any reactions where you have the biomolecules, so like bigger molecules versus the nucleotide, or like oligomers, but different size, like molecular, in terms of molecular weight or density. So in that case, suppose you have a big molecule, you have another big molecule, and you have another big molecule. In terms of molecular weight, suppose it is 1050 and it is 850 and it is 600. Okay, and now you can do the DOSY NMR, and in DOSY NMR it will show you the all of that proton, whatever the molecules has, all of that proton, every proton here. Okay, but in the field you will see some of the proton like this. Okay, so like this. So if you think, like if you can draw a line on those peaks, so you can say there are 3 different lines you can draw. Okay, 3 different lines you can draw here. So this peak is corresponding this peak and this peak, and this peak. Okay, so you can say easily these three peak is for a same compound. Suppose compound A, and these three peak is another compound. Suppose compound B, and these two peak. Maybe I can draw another. So these two peak, really. So maybe you can add one more peak here. Okay. So these two peak is another compound, that is C. Now, based on the molecular weight, so you can determine which one is what. You can watch my previous video on DOSY. At the end, I explained this part, but I will also tell, most probably the smaller molecule will come first than the bigger molecule, like larger molecule, based on the density and other molecular weight, or vice versa, maybe the reverse. I need to recheck. So I'll tell you, or you can ask me in this video, or also my DOSY video, so you can get the answer. So definitely I explained there, I remember. So hopefully the theoretical background or discussion will help you a lot to understand the COSY, NOESY, HMBC, HSQC. Another day maybe I will discuss about the DEPT or depth 135 and depth 90. So now I'm going to show the real application of those. Since it is too long video, maybe you will see my next video, like part 2 video of HMBC, HSQC, NOESY and COSY. So up to then, stay fine and thank you for watching my video. Bye now.